there any questions? You look like you're ready to ask something. Okay. Okay. What is Newton's second law of motion? It's what I've referred to as the most important equation in all of physics. Denise?
F equals mg.
The weight equals mg, but that's a specific case for Newton's second law.
Would it be F equals MA?
That's the one. And what is A?
Slash
I think it was said. M?
mass
With confidence.
mass
F?
force.
More specifically?
Total.
That's it. Sasha, say it again? Yes. So, in the lab that you did last Thursday, we had a cart attached to a string, another mass hanging down here. If we looked at this, at the forces acting on that cart, actually let's do the force diagram. Because we can. So we've got a cart, string, let's do the full force diagram here. And ground. Force diagram, we'll put up F-town in a Saturn center marker. What force is acting on what? Assume ideal string. Anyone? Jump right in. I have a feeling that several of you in here, if not all of you, know something but are just afraid to speak. Don't worry.
Normal force.
Pardon?
Normal force.
Acting on what?
The cart.
Acting which way on the cart?
Down.
The normal force is pulling this thing down? What's exerting the normal force on the cart?
The table.
McKenna?
The table.
Yes. Which way is the table exerting that normal force on the cart?
Upward.
Yes, there we go. Yes. The normal force is what keeps one object from going through another. So the table is pushing up on the cart to keep the cart from going through the table. So we've got a normal force acting up. And since we'll have more than one, we'll just label this Y sub C for cart. They come in pairs. Where's the other one of those?
Table and the ground.
Other part of that pair. There's going to be a normal force pair between table and ground, but not there yet.
Would you write down on the table?
Yes. All right, so the table's pushing up on the cart, cart pushes down on the table. The fact that they come in pairs and each part of that pair acts on a different object, Newton's third law of motion. And because they should be the same length if I was being really picky about it. Okay, another pair of normal forces.
The table on the ground.
All right, which way is it acting on the table?
Down.
So the ground's pulling down on the table?
Or up. Like.
It's one of those two.
Pushes down.
Say it again?
The table pushes down on the ground.
Table does push down on the ground. So Y's T. And,
On the table.
yep. I don't have to put one on each leg, because presumably the table has 4 legs, so I'm not drawing 4 of them. So that's sufficient for up on the table. We've got another pair of normal forces. I'm going to perhaps spoil some of it by, there's a pulley there.
Is it the rope on the floor?
Yes, it is. Which way is it acting on the rope? Normal forces are always, when I draw them, if I draw them in relative positions like this, they will always be opposite each other. They will always point away from each other.
So the way that way and the rope that way.
So on the rope that way? Okay. Yeah, there's a reason the rope is bent like that as opposed to straight down. So I've got this normal force acting this way, we'll call it Y sub R, and then this way on the pulley. There we go. Anything else touching? I think that's it. So the cart was on the table, yep, all right, there we go. Normal force, done. That was the bad one. What next?
Wait,
Okay, acting on what?
the table and the ground.
Okay, which way does it act on the table?
Table going down and the ground going up.
All right, so there's weight acting down here. That's weight up table, and then there's one acting up. And next,
The cart and the ground.
okay? Acting which way on the cart?
The ground.
And the way I've drawn this, the cart weighs more than the table. And anything else?
The box,
Okay.
weight, okay.
Do B for box. All right. Anything else? Any other weights? Logan says no. I'm not sensing any sense of confidence over there, Logan, when you shook your head.
What is the pulley count?
Because I've drawn the pulley attached to the table, the pulley is part of the table. If you want to do a weight of the pulley, you can. I would not, if this were a, say, a test problem, I would not take off for that. It's just not necessary since I can count it as part of the same object. All right, rope's ideal, so nothing, don't have to do it for the rope. Again, if you did a weight for the rope, yeah, it's, in reality, it's there, but we're ignoring it. All right. That is supposed to be a P there. Weight is done. Logan was right. Well, you've got 3 other letters to go. What about other? You've got one head shaking no. You've got wards, seems to be a groundswell of 3. Okay. there's no other. Tension?
Yes.
Okay, which way is it acting on rope?
Pulling down.
Wait, pulling down on the rope? What? You pointed that way and then you said, then I heard you say down, so,
Oh, because it goes like this.
okay, so how about this part of the rope right here, which way is it acting?
On the cart.
Okay, it is acting on the cart, which way?
Towards each other.
Okay. And here?
Towards each other.
What about at the other end?
The rope towards the box and the box towards the rope.
And since it's an ideal rope, the tension is the same throughout. So so I don't need a subscript there. Tension done. That one.
There's friction on the pulley.
Ideal.
The cart and the table.
Okay, cart and table. Again, we're gonna assume ideal, you're using a super pulley, so no friction in the pulley and the bearing, and ideal rope, it's frictionless, so it's not, the pulley actually doesn't turn in our nice ideal board situation. All right, so which way is it acting on the cart? Because the cart wants to go that way, friction is acting opposite that, so we got friction acting this way. It's what causes the wheels to move. F sub C for cart, and which? And there is another pair of frictions.
Table is brown. Table is brown.
Yes. Which way is it acting on the table?
Table on the ground is
Friction's acting that way?
on the ground.
On that way on the ground, this way on the table? That was my first thought, but then I began to realize I got friction going this way, but I also have a part of this going that way. And let's see, as that moves this way, table would have to move. In reality, in this particular situation, this is gonna overpower that. So the friction actually would act that way. But I didn't give you enough information here really to determine that. Make sure my F looks different, not so it's not looking like that F. But if you had friction going the other, let me just take another moment here just to think through this. So as the current moves that way, it's a closed system horizontally, so if the current moves that way, the table has to move that direction. Yeah, feeling confident about this. All right. Now, in the lab that you did last Thursday, we assumed that this was minimal. That there was really, we didn't worry about the friction because we had some nice carts, and so the friction that would be acting at the axle of the wheels causing a loss was minimal. So I'm gonna plug in the F equals MA for my two objects there, for my cart and this mass friction. So I'm gonna ignore friction, just because I'm gonna extend it in a moment, but, so if I looked at horizontal cart, I have one horizontal force, tension, and that's gotta be equal to the mass of the cart times whatever the acceleration of the cart is. If I look at the vertical of the box, well, I got two forces vertically. Which way is it going to accelerate? Just physically, which way will this accelerate?
Towards the ground.
Yeah, I hope so. Or get one more Nobel Prize for one of my students because of results coming out very strangely. All right, so we have weight going down, we have tension going up. So I have weight of tension minus the friction, because that's going the opposite direction, is equal to the mass of the box times acceleration. So I'm using F equals ma, just breaking it down into horizontal and vertical. Whatever this tension is right here, it's the same tension as that. This is the nice part about, we're assuming an ideal string there in the lab, and so this tension is the same, so whatever this is, it's the same as that. So I have this weight acting down. That is, let's see if I can do it slightly better than that. So I have the weight of tension minus the, try that one again. Weight of, that should be a B there, not a T. Sorry about that. It really doesn't look like anything in there. That is. So we have weight of the box acting down, and then we have tension acting up, and that's mass times acceleration. All right, since that tension is the same as equal to this, that's what the math people say equals is, so whatever that is, this is on the other side, so that's weight minus MdA in. I'm making all sorts of mistakes today. MCA equals MdA. Now this is a more formal way of doing what we talked about on Thursday, but there's a reason I'm going through this. Now I have this, whatever that's some number. If I add it to both sides, I get rid of it from the left-hand side and bring it over to the right-hand side. So I end up with W sub B, weight of the box, is equal to mass of the box times the acceleration plus mass of the cart times acceleration. I'm gonna do one more step. And if you're feeling overwhelmed, just deep breath. This is, I usually don't go through this level of detail, but again, there's a reason for it. Weight of the box, I'm gonna factor A out, MD plus MC times A. This is what we did on Friday where we had the weight of the box, and we had the total mass that's being moved, and we tried to figure out if this was accurate. We did a plot of acceleration versus force. So that's the force, that's the driving force that we did, that's the acceleration which you found using the sensor. And tried to see, is that the inverse of the total mass that's being moved? I know what you're thinking. You're saying, hey, why couldn't we have been doing physics all along with no numbers? Yeah, you're right, we could have. All right, questions to hear? So now, suppose I get rid of the wheels. And this box is just being dragged on the table. What would change in our force diagram?
Would the forces of the cart flip?
Which forces.
Oh, like acting on the card.
Would they,
Would they flip? The
uh,
card
is-
would be,
the rope is still pulling it that way. Normal force is still holding it up. The weight is still down. And friction is still opposing the motion. So the forces would stay the same with the cart. So what would change?
no,
There we go, that's right. Nothing changes. The only difference is that now friction pretty much changes. We can't ignore the friction, but the force diagram stays the same. So now we have to worry about over here. We now have minus friction. And so this tension here, add friction to the other side. So if I had x minus 4 equals 7, to get x by itself, I add 4 to both sides. I'm just doing the same thing here, except with letters. I'm just bringing this over, adding this friction to both sides. And so this now becomes friction plus MCA. And I'm gonna keep that minus F there and then minus F there. So now my total mass times acceleration is the weight of the box minus this friction. So let's talk about friction. How many of you have seen the friction video? Well, you're in for a treat, no doubt. Don't forget, watching the videos is part of the course. Why is there friction? What causes friction?